Assalamualaikum and good day everyone. In this video, my friends and I will explain how to find the least square solutions for the equation ax equal to b, where a is a 4 by 3 matrix and b is a 3 by 1 vector, as you can see in the slide. I will be presenting the hand calculation part. So for the first step, we use the Gram-Schmidt's process to find an orthogonal basis. In this case, we let x1 be the first column vectors of matrix A, x2 be the second column vectors of matrix A, and x3 be the third column vectors of matrix A. This step is important because it ensures that our basis vectors are mutually perpendicular, which makes the later calculations simpler and more accurate. After that, we continue with the Gram-Schmidt's process formula to construct the orthogonal vectors. First, we define v1 to be equal to x1. Next, we calculate v2. This is done by taking x2 and subtracting the dot product of x2 and v1. Divide it by the dot product of v1 with itself and then multiply by v1. Finally, we'll calculate v3. This is done by taking x3 and subtracting the dot product of x3 with v1, divide by the dot product of v1 with itself, and multiply by v1, and then minus the product of x3 with v2, divide by the dot product of v2 with itself, and multiply by v2. This step-by-step process ensures that v1, v2, and v3 are all orthogonal to each other. Next, we now substitute the values of x1, x2, and x3 into the Gram-Schmidt's formulas to find the orthogonal vectors v1, v2, and v3. We will round each value to 4 decimal places to keep the results consistent and precise. We will get v1, v2, and v3, which each of it is a 4 by 1 column vector, where v1 is 2, 7, 4, and 3, v2 is 3.1282, negative 2.0513, negative 0.7436, and 3.6923, and v3 is 2.2348, 0.5264, negative 0.7279, and negative 1.7475.
To find the orthonormal, first we must find the norm, also called the magnitude or length. The formula for the norm of a vector is the square root of the sum of the square of its component. First, we calculate the norm of v1. We take the square root of the sum of its component squared. This gives us 8.8318. Next, we find the norm of v2 using the same technique as v1, resulting in a norm of 5.3084. We calculate the norm of v3. This calculation gives us a norm of 2.9757. To obtain a unit vector, we normalize the vector. Normalization means dividing the vector by its norm. We define u1 as v1 divided by the norm of v1. Substitute the value and the result of u1 is 0.2265, 0.7926, 0.4529, and 0.3397. Similarly, we normalize v2. We get 0.5893, negative 0.3864, negative 0.1401, and 0.6956. Next, normalize v3 and we'll get 0.7510, 0.1769, negative 0.2446, and negative 0.5873. By placing the orthonormal vector as column of a matrix, we form the matrix Q, which is orthonormal matrix.
After we find the orthonormal vectors, we proceed with the QR factorization. We let matrix A be equal to QR. Then, to isolate R, we multiply both sides by Q transpose. This gives us the formula R equal to Q transpose multiplied by A. After carrying out the calculations carefully, we obtain R. This result is an upper triangular matrix as shown in the slide. This step is important because QR factorizations allow us to rewrite the original matrix A in terms of an orthogonal matrix Q and a triangular matrix R. which makes solving least squares problems much easier.
Now consider the original system AX equals B. Substitute A equals QR, we obtain QRX equals B. Multiply both sides by Q transpose, we get Q transpose QRX equals Q transpose B. Again, since Q transpose Q equal identity matrix, the equation becomes Rx equals Q transpose B. Write the system explicitly. Matrix R is an upper triangular matrix as previous slide. This matrix multiply the vector x1, x2, and x3. Next, we compute Q transpose times B. Matrix Q transpose consists of the orthonormal vector, and vector B is 7, 6, 8, 2. After performing the matrix multiplication, we obtain the vector 10.6437, 2.0771, 3.1870. Since R is an upper triangular matrix, we solve this system using back substitution. First, we solve for x3 using the last equation. Then, we substitute the value of x3 into the second equation to find x2. Finally, we substitute both values into the first equation to find x1. After performing back substitution, we obtain the solution vector. x1 equals 1.5197, x2 equals negative 1.1084, x3 equals 1.0710.
So next, I will talk and explain about how to solve this question using mathematical software. So first, we have a linear system AX equals to B, and if we observe the dimension of matrix A, it is 4 by 3 matrix, which is 4 rows and 3 columns, and while vector B is 4 by 1. So this means we have more equation than variables, so it is an overdetermined system. So an exact solution often does not exist. So we need to find the best approximate solution using the least square method. So how to solve this by using Mathematica? So first step is to define the equation in the software. First, we use curly braces to define each row. So in Mathematica, matrices are represented as a list within a list. So for matrix A, we enter it row by row. So first row is 2, 6, 9, followed by the next row, and we end the line with a semicolon. So next, to verify our input data, we use the slash matrix form, and to comment the display the data individual matrix structure we are input in the software. So on the right, we can see the output. This allows us to compare the matrix we enter in the software, then the actual question that we have. So once we are confident that the matrix A and the vectors B we put are correct, then we can move to the next section. Moving on to the critical step in the least square solution is to finding the orthonormal basis for the column space in matrix A. So mathematically, this is often associated with the Gram-Schmidt process to obtain the matrix Q. So here we define the matrix QQ, and you will notice the syntax is transpose bracket organized bracket transpose A. So why do we need to transpose twice? So the reason is that orthogonalized comment in Mathematica works on rows. However, we want to find the orthonormal basis for the column of matrix A. So therefore, we flip the column to row first and perform the orthonormalization. Then we flip them back in the original form. So we get the output is on the right form. Next, we move to the section number 2. So we use the NQQ command to convert the symbolic form into numerical or decimal values. So and we also use the number form with the setting infinity, 4 to display in just 4 decimal places. And now you can see our orthonormal matrix with easily and readable decimal values.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firas bin Badrusham. So for my part is finding QR factorization. To begin, I define the vector B and the coefficient matrix of M. This is an overdetermined system because we have four equations and only have three variables, meaning we are looking for a least square solution. So as you can see, the first thing I do is QR equals to QR decomposition bracket M equals to system 4 by 3. Then after performing the QR decomposition, I specifically call the matrix Q and apply it in a matrix form. This isolate the orthonormal component, allowing us to see the unit vectors that form the basis of the subspace. Similarly, I display the matrix R in matrix form to highlight its upper triangular properties, which simplify the process of back substitution when solving for our variables. So, for this part, the code is x equals to inverse R dot Q dot B. I define the solution vector x using this formula. Mathematica ensure that there is no rounding error occurs at this stage, as it carries out the form of Q and R in matrices. After I calculate the vector of x by multiplying the inverse of R with the product of Q and B, I choose to keep this in exact form, first to maintain mathematical precision before moving to a numerical approximation. The code is map bracket matrix form QR. By mapping the matrix form function over the list containing both Q and R, I can present a side-by-side comparison of the two components to verify that the decomposition has been executed correctly. The next part is x equals to n bracket inverse R dot Q dot B. We get the matrix and we transpose it to Q dot R. After that, we code QQ equals to transpose bracket orthogonalize bracket transpose M. We do this to double check the result. I manually created an orthonormal matrix QQ using the orthogonalize function on the transpose of M. This serves as a manual verification of the QR decomposition. Finally, I derive the RR matrix using the pseudo-inverse of my manual QQ matrix, solving for x using the alternative to get the exact same numerical result, confirming that our least square solution is accurate across different methods. So, for the final answer, for the Mathematica, I get the x1 equals to 1.5199, x2 equals to negative 1.1085, and the x3 equals to 1.0710.